All right, this is video 14 for the baby real analysis series, and in this video it covers subsequences. And so suppose you have some sequence yn, and you have the indices n1, n2, ... and then less than nk, and then less than nk plus 1 keeps going. And let those be natural numbers. Then the set of all the ynks as a subscript is a subset of the sequence yn, and it's called a subsequence. As an example, if we had the sequence where it alternates between 0 and 1, where it's 0 for the odd index, and then even or is 1 for the even index. So let's say that's your sequence where it alternates between 0 and 1. And then it doesn't converge. We can form a subsequence from this sequence that does converge. We could take all of the values that are 1 and make them into its own subsequence. Well, all the values 1 correspond to indices that were even numbers for the original sequence yn. So that's why it has the subsequence of 1s, which we know converges to 1 because it's a constant sequence. Then the subsequence would be y subscript 2n, so 2 times n for the even values of the indices. So that's an example of a sequence. We produced a subsequence of the even terms, where the even terms themselves form a convergent sequence, subsequence. As another example, let's say you have the sequence of n squares. So the squares, so we have 1, 4, 9, 16, and I'll list a bit of them. So then next one's 25 and 36. And I go up to 100, and then 64, 81, and 100. All right, so let's say that's our sequence, AN. And then let's say I pulled the values that were the even terms. It follows that a subscript 2n. All right, those are the indices that have even values. So like this is index 2. This has index 4, index 6, index 8, index 10. All right, so that's like A2, A4, A6, A8, A10. So we can form a subsequence, and that's going to be 4, 16, 36, 64, and then 100, and keeps going. All right, now that also doesn't converge, right? So this diverges. So it doesn't have to be that the subsequence converges. That was just an example that I found a subsequence of 1s from this sequence that's alternating between 0 and 1 that does converge. Right now I'm just pulling the terms with even indices. And that's to be 4, 16, 36, and so forth. As another example, if I pulled the terms where it's a subscript 4n minus 3, you'll have the following. So it'll be like 1, 25, 81, 169, 289, then keeps going. And as far as what these were in the original sequence, This is A1, this one's A5, and that's A8, and then A13, and then A17. So that's just another example of a subsequence where you pull in with the indices 4 and -3. All right, now see that diverges too. So those are just some examples of subsequences. Now I'm going to go on to the next theorem, which is called the Monotone Subsequence Theorem. And the Monotone Subsequence Theorem says every sequence has a monotone subsequence. We call that monotone. You could be monotone increasing or monotone decreasing. And the proof of this is pretty clever. And I think I'll go to the picture representation, the idea first. So let's say you have this, so if you were to plot the sequence, and like this was like A1, A2, A3, and then this is A4 and so forth. So if you were to plot it, and then I drew these line segments, the yellow line segments are connecting the dots just to visualize better. And these values that I have in green, this A1, AN1, this AN2, AN3, AN4, AN5, AN6, so I'm pulling those particular terms out of the sequence. And notice these are high points to the what it looks like on the graph. So these are called peaks. So these are the peaks. To the graph of the sequence. And if I were to collect all of these terms that were peaks, notice I have it in this picture where it's decreasing, like AN1's bigger than AN2, bigger than AN3, and so forth. And you can continue this on forever when you have and this will be infinitely many peaks when it's going to be decreasing. Now here's a different picture, and in this picture, this has finitely many peaks. So we have, this is a peak. All right, so our sequence starts here. Okay, so I have these finitely many peaks. After I go from the last peak, then I can form a subsequence that you see in green, where I'm picking the terms AN1, AN2, and so forth, and notice that it's an increasing subsequence when I do that. All right, so the idea for the proof is to rely on this thing called peaks, and we're going to have to formally define a peak. And after we formally define a peak, we have two cases. One of the cases right here is when there's finitely many peaks. And once you hit the last peak, we can form a subsequence after this last peak, where the subsequence A and K is an increasing subsequence. For the other picture, we have infinitely many peaks. And for infinitely many peaks, we have a subsequence AN1, AN2, and so forth that is decreasing, monotone decreasing. So those subsequence itself, A and K, are the peaks of the sequence AN if there were infinitely many peaks. So we either have finitely many or infinitely many. If there's infinitely many peaks, we just collect all the peaks and form a subsequence of those peaks, and it forms a decreasing subsequence. In the other case, if you have finitely many peaks, if there's finitely many, then collect the terms of the sequence that come after this last peak, such that the subsequence is going to be an increasing subsequence. in either case, whether it's finitely many or infinitely many, we've produced a subsequence that's monotone. It's either monotone increasing or monotone decreasing. All right, so that's the idea. Now the actual proof. All right, so proof, you're given a sequence yn. And again, we're trying to show that every sequence has a monotone subsequence, and we're going to rely on this concept of a peak. So define the nth term ym to be a peak if for all n bigger than m, we have ym greater than or equal to yn. And so, in other words, ym is called a peak if every successive term is less than or equal in size. All right, that's what we're going to say as a peak. An increasing sequence is going to have no peaks since each successive term is larger than the previous. But a decreasing sequence will have infinitely many peaks since each successive term is smaller than the previous. That's why when we had the picture where we had our increasing subsequence, those were not peaks. These were not the peaks. Whereas when we had this one, we had a decreasing subsequence, that was all of the infinitely many peaks. Okay, so the subsequence itself, if the subsequence itself is increasing, then that means it's going to have no peaks. Right? Because based on the definition of what a peak is, the nth term is such that every successive term is going to be less than or equal in size. But for increasing, each successive term is larger than the previous, so then there's no peaks. All right, so now that we've defined a peak, now there's either going to be infinitely many peaks or finitely many. If there's infinitely many peaks, then let yn1, yn2, ... yn be the peaks of the sequence for the set of the yns. So then by our definition of peaks, we formed a subsequence where it's monotone decreasing, right? Because we have yn1, it's going to be greater than or equal to every successive term. If I collect all the peaks, so starting with the first peak, it's going to be bigger than the second peak, bigger than the third peak, and so forth, and keeps going on forever. So that's what it is when we have infinitely many peaks. So this subsequence yn is a monotone decreasing subsequence. Now the second case is when we have finitely many peaks. So let's suppose that for the finitely many peaks, you label them ym1, ym2, ... up to ymk. So that's going to be your finitely many peaks, where the indices mk is less than mk plus 1. Let capital N be the max of these indices. So let's m1, m2, ... mk. So let it be bigger than the max, sorry, not the max. Let capital N be the index that's bigger than the max index for the peaks. So that means it's going to be the first index of the term that comes after the last peak. So in this case, since it's this index does not correspond to any of the peaks, then y cap subscript capital N is not a peak. And if it's not a peak, then there's going to be another index n1 greater than capital N, such that yn1 is greater than or equal to yn. Likewise, this yn1 is not a peak. And then also find the n2 bigger than n1, such that yn2 is bigger than or equal to yn1. And yn2 is also not a peak. So in general,ynk is not a peak. So there exists a subscript or indice nk plus 1 that's bigger than the index nk, and ynk is less than or equal to ynk plus 1. So we have it such that we have y capital N as our index, and then less than or equal to yn1, less than or equal to yn2, so forth, and then this goes on forever. And then we basically produced a monotone increasing subsequence y and k. Again, I think it's easier to visualize right here. So we have our last peak is 6 is the index. So any index beyond this any index n bigger than 6 is not going to be a peak. All right, so then collects all of the terms where we form a increasing subsequence, and all of the terms from this increasing subsequence is not going to be a peak because it's increasing. All right, so that's what's happens in this proof. So we've shown that whether yn has infinitely many peaks or finitely many peaks, and regardless, yn has a monotone subsequence. All right, so that is the proof for that. And I already went over this picture. Now this leads me to the next thing, the Bolzano-Weierstrass Theorem. Not sure if I'm pronouncing that correctly, so my apologies. But it just says every bounded sequence has a convergent subsequence. And the proof of this is really simple. So proof. Let's see. So hold on a second. All right, so let the subsequence an be bounded. What did we show in this previous proof? We showed that every sequence has a monotone subsequence. So this sequence an has a monotone subsequence by the monotone subsequence theorem. By M sub t, there exists an A and K subsequence where A and K is monotone. So since our sequence AN is bounded, so is our subsequence A and K. And we know that if a sequence is bounded, if we have a monotone sequence that's bounded, then it converges. We know that a monotone sequence that is bounded converges. And I believe that was the monotone convergence theorem. All right, so in other words, our subsequence A and K converges to some A and the real numbers since it's bounded and monotone due to the monotone convergence theorem. And that's it. We've produced a convergent subsequence from a bounded sequence. So proof. is done. So I think that's where I'll stop it for this video, and next video I'll talk about Cauchy sequences.